can start with the first talk by Pavel Kroupa from the Bonn University, Germany. The talk is about current problems of ΛCDM on small scales, open stars, clusters, and the absence of halo dynamical friction.
Well, hello, great to be here, and thank you for organizing this meeting. And to let me begin, the file uploaded contains more material than I'm presenting here because Elena told me the talks was supposed to be only 10 minutes, so I hope to hold those 10 minutes. It's split into two parts. The one is to test for the existence of dark matter in a very robust way. And then the second part is to apply that to understand what the implications are. So one can test for the existence of dark matter very simply using Chandrasekhar dynamical friction, simply meaning from a conceptual point of view. Of course, from the data point of view, it is not so trivial. And so why can we use this Chandrasekhar dynamical friction? First of all, if Newton-Einsteinian gravitation is correct, then in the standard model of cosmology, which builds upon that, each galaxy is surrounded by a dark matter halo, and there's no escaping of that because that's the fundamental property of this theory. So there's a much, much larger dark matter halo around the galaxy we see in stars and gas. And so if a dwarf galaxy comes in to this dark matter halo, the dwarf galaxy itself has a dark matter halo, it will lead to an interaction with the dark matter halo, a gravitation interaction. And this is extremely well understood. So we have here the dwarf galaxy with its dark matter halo in the dark matter halo of the large galaxy, and these are the dark matter particles. And that each dark matter particle is on a ballistic orbit and is deflected by the propagation of this dwarf galaxy on its orbit, such that behind the dwarf galaxy one builds a wake of dark matter. And so this is a visualization of the effect that this wake pulls back at the galaxy and decelerates it. In reality, what one has to do is one has to integrate over all satellite dark matter particle encounters. You can imagine there are a huge number of them, but this is an integration over all these encounters over all distances to calculate the transfer of linear momentum from this galaxy onto the small dark matter particles. So essentially the dark matter halo of the host galaxy absorbs the kinetic energy of the incoming satellite. This is known, calculable through this type of formula here. This is the Chandrasekhar dynamical friction. And you note, so the deceleration here of this velocity depends on the velocity of the satellite cubed, 1 over the satellite velocity cubed, times then all these parameters here. So it's actually 1 divided by velocity squared, because we have here the quantity of the velocity 2. And then it's also proportional to the mass density of the dark matter halo. So this m is the mass of the dark matter particles here, and rho 0 is the number density. So this quantity here is fixed by the model, by the CMB essentially Big Bang model, so by the ΛCDM model, which is fit to the CMB properties. And so this is not a free parameter one can choose. So this test is insensitive to the mass of the particles. It's only sensitive to the mass density of the dark matter, fixed by the model. There seems to be some echo. And so we have now the situation that the satellite galaxy creates this wake and then decelerates, and therefore it falls towards the center rather than being on a hyperbolic flyby, which we would have if there were no dark matter. And so we can now test whether the flyby velocities are small, given this effect of deceleration through this dynamical friction. And this is why galaxies merge, but only in the dark matter theory, because if we have a theory without dark matter, they would typically fly past each other on hyperbolic orbits. And here's an example of two galaxies merging, which you can see how quickly they merge. It's basically within a crossing time. And so this transverse dynamical friction is very well understood, and we can apply this now explicitly. Here's just one test which was applied by Gary Angus et al. In the year 2011 already. So we have here from the theory of lambda CM structure formation, the mass of the galaxy. For example, our Milky Way would be around 10 to the 11, somewhere up here in stars and gas. And the dark matter halo mass of this galaxy is on this axis. So our galaxy would have a dark matter halo mass of a few times 10 to the 12 solar masses, somewhere up on this end, according to the theory. Now, we can't vary this at will at all. There's a small range of variation, simply because each galaxy has a different merger history, but we cannot change this number, this correlation between the baryonic mass and the dark matter halos as we wish. Okay, that is fixed by the theory up to this variation. Each of these points is a galaxy formed in one of these simulations, which are listed here. And so if you look at the satellite galaxies here of the Milky Way, we know their distances from our galactic center, we know their velocity vectors, and we know their luminosities. And so the luminosity reflects the baryonic mass of these objects, which is below about 2 times 10 to the 6 for these here. And therefore, the dark matter halos these satellites are allowed to have are confined to this region here. However, now, this is the condition that we have our Milky Way and the satellite comes in the theory, and it will not be allowed to be on hyperbolic orbit, so it would fly away because it must be stuck, because it has to become a satellite, so it must get stuck. So we can calculate by dynamical friction which dark matter halo do I need to get these satellite galaxies stuck in the Milky Way so that they don't fly out again. And that means we need this dark matter halo for each of these for them to get stuck. Otherwise, they wouldn't be on these type of orbits and they would be receding from the Milky Way. While the fact that they have these dark matter halo masses we are forced by the theory to be in this regime. And so this regime, these two are incompatible. So in order for them to get stuck, I need a much more massive dark matter halo than the theory is allowed to give me for that mass of the satellite, right? And so this basically tells us that there's no in-full solution for them to get stuck given their observed properties, and therefore they can't be dark matter halo. So that's one test. And of course, we can look at a large imaginary cloud and small imaginary cloud. Here we have the imaginary extreme, that's the Milky Way, and calculate their orbits, assuming they are dark matter halos. Now, the calculations, which are in this upcoming publication, we can see that, so this here is the gravitational attraction if the LMC is away from the SMC at 10 kiloparsecs. And this here is the dynamical friction force of the LMC on the SMC and SMC on the LMC, because they are both in the dark matter halos of their own dark matter halos, and these two dark matter halos are inserted in the dark matter halo of our Milky Way. And you can see that the gravitational attraction between these two galaxies and the dynamical friction force are comparable, in scale. This precludes orbital solutions. So no orbital solutions, because the LMC and SMC would just merge far too quickly. Now, again, that rules out the existence of dark matter halos. And then we have these nice tests here on the bars of the galaxy. So a bar of a galaxy is rotating in the dark matter halo of the galaxy, and the dark matter halo therefore absorbs through the torquing the angular momentum of the bar, so the bar should get slower and then shrink in length, and that is not seen as this detailed observation analysis shows. This is a more than 5 sigma disagreement between the dark matter models and the observed galaxies concerning these bars. And then another test by these 3 publications tells us that this group of M81 with its fairly major satellite or companion galaxies would merge within 1 billion years, but we need significantly more than 1 billion years to produce all these gaseous streams through encounters. And so again, this existence of this system does not allow them to be in dark matter halos, because the dynamical friction of all of these in their dark matter halos is just immense, so that the whole thing should be merging within about 1 billion years, which is not observed. And so there's no dark matter, and therefore we must use a different law of gravitation. Okay, so this existence for dark matter test is independent of any idea of an alternative theory of gravitation or of MOND or so. But since there is no dark matter, then we must therefore change the law of gravitation. So different than Newtonian dynamics of gravitation. And here we are at the currently testing MOND, and here one could argue, first of all, going back historically, how was the current understanding of gravitation developed? It's based on the work of Newton in the 17th century, who took the data from the solar system, inner solar system mostly, and then Einstein in 1916 reformulated this in terms of a space-time distortion, but still solar system data, because at the time of Einstein, galaxies had not been mapped out. They were not understood what galaxies were, so Einstein had no chance to improve the law of gravitation beyond the reformulation as a space-time curvature. And so I think I'm running out of time, right? You want only 10 minutes?
Yes, 1 minute more, please.
Yeah, then well, then I will not get to the tidal test. It's okay. This is an important Gedanken experiment, which actually goes back to Indra Banik. And so we have here the trampoline. And if you put weights on the trampoline, so heavy weight gives a larger depth. Depth goes up, so the depth will be larger. A smaller weight, smaller depth, and smallest weight, small depth. We can then call this our law. Extrapolate it. Will it work? It won't work, because at some very small weight, of course, the fabric, the material structure of this will play a role, right? And so this empirical law here breaks down at very small weights. And basically that's what we are saying, and that's what MOND is telling us, that when we go to space-time curvature, which is extremely small, additional effects seem to play a role. And that is encapsulated by the formulation of MOND. And just as a brief, I'll just skip through to the final slide here then. So the tidal tails of star clusters, so stars leave the star clusters through tidal tails. And in Newtonian gravitation, the number of stars is symmetrical, same here as there. In Newton, we have more here, and that is indeed observed. Right, so this actually tells us that MOND works on these parsec scales and correctly predicts the overabundance of stars ahead of the leading motion of the cluster compared to the back. So I think I'll end here then.
Okay, thank you. Thank you very much for the very interesting exposition. We can continue with the discussion, and we have a few questions collected from the last weeks, and maybe also for the in live from the attendees. The first set of questions is about the paradigm shift. For example, four questions related to this issue. I am reading now. Does the recent discovery done by James Webb Telescope prove that the lambda CDM model needs to be updated or completely rejected? I think is less most answer, but you can comment something. Other similar question is, as a whole, cosmology is in such a state of despair seems like there might be underlying more than fundamental assumption that needs abandoned. Do you think that is possible to revision of only a fundamental assumption could be resolved most of the problem of cosmology? are the first principal alternatives to lambda CDM with no additional free parameters. And the last question related to the paradigm shift is, one could also ask whether there are any alternative way to think about the universe other than lambda CDM. What are the alternatives for this?
Well, so I wrote down some answers into the sheet, right? And those are all very deep, very important questions, and that's what we are, of course, working on. So the JWST observations currently, as far as we know, they do indicate that the galaxies between a redshift of 10 and 20 are far too massive compared to lambda CDM. And so, yes, that is yet another stress point for the theory. One could envision that a top-heavy IMF might partially alleviate the problem, because then the galaxies are less massive and they send out more light. And if you assume the stellar IMF is invariant, then one would infer them to be too massive. In fact, if the galaxies have a top-heavy IMF, then for the same light we get less mass. So that is a possibility, but this doesn't really work, I think, but it hasn't been fully calculated, because the structure formation with a varying IMF would be different, because the feedback would then be stronger, and so it will actually be harder to form more massive galaxies because of the stronger feedback, right? At low metallicity, if the IMF becomes top heavy. So yes, it seems that the JWST observations are indeed another nail in the already closed coffin of lambda CDM. I mean, you can keep on adding nails into that, as you can spend the rest of your life hitting nails into that coffin. But it's and that's what these other questions are now indicating. We need to go away from that coffin, put it into the ground, and start thinking about a completely new theory, right? And from what we are doing here in Bonn, in Prague, St. Andrews, and Nanjing, is to base our work on MOND, because MOND has an incredible track record. In fact, to my understanding, MOND is the one theoretical description of gravitation which offers the greatest number of predictions which have been verified. And this goes from gigaparsec scales, surprisingly. I mean, in MOND, we don't have a Hubble tension. In a MOND cosmological model, we don't have a Hubble tension, so this is one aspect, and down to star cluster scales, and even into the solar system, where we see the Kuiper belt objects having in a MOND-like. Then there's the wide binary test, which of course is an issue now, thanks to Indranil. Thanks, Indranil, who's connected. But yes, the overall, I think MOND seems to be the current correct direction, and so that's what we're investigating. And the cosmological models we are building based on MOND, so no dark matter, appear very, very promising. So what is the explanation for the bullet cluster and similar observations in Milgromian MOND gravity? So that's the terrain of Elena, of course. But don't know, Elena, do you want to say something to this, or shall I continue monologuizing?
Whatever you prefer. If you like to say the question, that's fine.
I can give my way of answering it, and that is just to say that this was one of the greatest PR gags by the dark matter community, and PR gags are always dangerous. It's so in Milgromian gravitation, it works in the sense that we get the velocities and the timescales right, and the fact that we even have these massive clusters. El Gordo, that's Elena's specialty in particular, actually works fine in Milgromian gravitation in terms of building the clusters and having them collide, pass through each other with the observed velocities. I mean, with the deduced velocities. There's a slight tension with the mass in the clusters, which, however, depends on how one calculates the masses of the clusters, right? And that then is an issue of what tracer do you use. Do you use weak lensing? Yes, maybe that's a good way, but weak lensing in which theoretical framework? In Einsteinian gravity? No, because that's been ruled out. So you have to do weak lensing analysis in a MOND relativistic theory. Has anybody done that? No. So therefore, that particular way of arguing that Milgromian gravity would be not compatible with bullet clusters too stupid, basically, because you have to be consistent in the theory you're using. And so The work we have done, especially now based on what Elena has been doing, clearly shows that bullet cluster and the El Gordo cluster work well in MONDs up to the point that maybe there is some tension with the mass in these clusters.
No, by the moment.
Yeah, I would like to ask one question. If
Yes.
people are also speculating about varying the fundamental constant, like Newton's gravitational constant, Planck constant. So, is it making some sense, or like, does this help anything to elevate some tension?
Well, it makes a lot of sense to inquire whether these fundamental constants are changing, because they might be or they must be coupled to the properties of the vacuum, and the properties of the vacuum are obviously apparently changing since it's evolving. So I think that's a very important aspect of this whole game. But for that we need some empirical evidence. I think, and currently there is no empirical evidence for any variation of these constants as far as we can tell. So what we are doing here in this grouping in Bonn, St. Andrews, Prague, and Nanjing is to assume these constants are constant, and see how far we get with that. I think Srikant has a question, maybe.
Yes. Srikant.
Yeah, hi, hello. Thank you for a nice talk. So my question is, how is MOND doing with the cosmological observations? Because I hear like some conflicting views in some papers, saying that okay, MOND is not in good agreement with the standard cosmological scenarios, or like in some dark matter observations. Because I'm not a person who works on MOND, so maybe how do you address?
Well, let me say it this way. Yes, MOND is in total disagreement with the dark matter model, and that's because the dark matter model is in total disagreement with the data. Right? So MOND is, as far as we have been testing, from gigaparsec scales down to the parsec scale, in excellent agreement with the data. There are some issues which still have to be resolved, and that is concerning the mass of galaxy clusters, which might indicate the evidence of a stellar neutrino. That could be the case. But as I'm saying, we need to understand what these masses of galaxy clusters mean in terms of the measurement, because the galaxy clusters are the largest structures which are visualized, partially visualized. Many of them might not even be visualized. They might not be in thermodynamic equilibrium. They're still in the process of formation. The boundary conditions are not well understood, since these things are in the process of formation. They're still assembling, and so deducing from a galaxy cluster by this factor of 2 mismatch, which is currently being discussed, is ludicrous given all the other evidence how MOND does so excellently. And then the only other tension is the wide binary test. Thank you again, Indranil, for who's published a paper arguing that it doesn't work. And there again, there are two teams claiming it does work. So MOND does extremely well. Newton is totally ruled out. Indranil found in his analysis, very, very large analysis, that MOND does not match the data, and we are in the process of trying to understand that particular issue. And the solar system, it seems to, MOND again seems to work, but in MOND is currently, it's a large framework, right? So you can use a particular formulation. I have it in the slides, but I didn't show it. You can use the Aqual formulation, which basically generalizes the Poisson equation in a very elegant manner, or you can use a QMOND version, which is a more not so nice way of writing down effectively MOND. The Lagrangians differ for these. There are subtle differences, especially in the transition region, when you go from the deep MOND limit to the Newtonian limit between these formulations. Then it's possible that MOND might be a modified inertia theory, which is an extremely theoretically very hard to formulation, which is very difficult to put into a computer. And at the end of the day, what we can only do is, in order to compare with the observational data, is to have equations of motion. We can code, right? And so we are forced at the moment to use basically Aqual or QMOND formulations, and they work as well as one can imagine any theory to work, given all these uncertainties, even in the data, right? So, hello, Tom. Nice to see you.
Hi, Pavel. How are you? The question is, what is your current explanation for the acoustic peaks in the cosmic microwave background?
It's a good question. I have never in detail studied that. And I was just going to say, but based on some of these questions in this spreadsheet, so there were some deep questions about a completely different model related to inflation, dark energy. And that's basically what this is about, right? So can we... so there's one way to doing a MOND cosmology, which has been goes back to Gary Angus and has been investigated by Katz et al. And then now most recently by Wittenberg et al. Here in Bonn and St. Andrews, where we assume that the lambda CDM expansionist is the same. So we have an inflation epoch. The CMB is the same as in the standard model. So the surface of last scattering and so there, these peaks are the same, have the same interpretation as in the standard model.
So that's dark matter.
So basically, in that, so that's the new HDM cosmological model, which has sterile neutrinos in abundance, as the lambda CDM model has in cold dark matter, which is a hot dark matter component, but the attractive aspect of that is that stellar neutrinos are less exotic than dark matter, than the cold dark matter particles, because the stellar neutrinos can be are more closely associated with the standard model of particle physics, right? Because you've got those three active neutrinos, which apparently change their masses as they propagate, and so there's a theoretical argument to say that there must be a fourth inactive neutrino version. That would be the stellar neutrino, and things seem to work out quite well in terms of the abundance of the stellar neutrino, the galaxy cluster mass mismatch. So Indra can actually say more to this than I, but this is a very attractive approach, and that would account for these for the properties of the CMB. However, that model seems to form structures too late and maybe form too massive structures at late times. Yeah, so there is some tension which is now being investigated, particularly also in St. Andrews. And so I'm taking this as a motivation to depart even entirely from that, to discard inflation, dark energy, and reinterpret the CMB to be something completely different. Yeah.
Yeah, so, I looked at neutrinos, HDM, for instance, and fit isn't quite as good as lambda CDM. You know, you could say it's rejected, but it's close enough that it's encouraging. What I actually did was think about magnetic seed fields in the early universe rather than MOND, but I mean, the point is the CMB does need some sort of dark matter, so you're just arguing against it on small scales, but on large scales you're accepting it, are you not?
Well, in the new HDM model, the stellar neutrinos would take that role, but it's a hot dark matter component effectively. But we are now asking other questions. So in terms of a radically different cosmological model, I call it the Bohemian model of cosmology. I don't at this stage want to give the details because it's being written up now, but that model gets rid of basically everything which is in the standard cosmological model, right? And that is a viable way to go too. But it hasn't been published yet, so I'm not confident at all that the CMB is what people think it is in terms of the surface of last scattering, because there's an asymmetry, there are issues with the properties of the CMB. Any model I know of which has been using the CMB as a boundary condition to calculate structure formation leads to a model universe which does not agree with the observations. So I have to change the boundary conditions, or I can think about changing the boundary conditions.
Okay.